Good evening, everyone. So, welcome to my YouTube channel, Maths Sapram. So, today we are going to see fifth lecture on linear transformation. Let's start today's lesson now. So, today we are going to do this theorem. Let V and W be two vector spaces over the same field F, such that dimension of V is equal to dimension of W. It means dimension of V and W are same and they are finite. It means V and W are finite dimensional and their dimension are equal. Okay. Then and T V to W be a linear transformation. Then T is 1 if and only if and only if T is onto. So proof. First assume that T is 1. T is 1. T is 1. Let dimension let dimension of V is equal to dimension of W is and that is finite. First assume that P is 1. Okay. Let's let B is equal to B1, B2 up to Vn be a basis for B. Okay. Then we claim that V dash is equal to TV, image of basis B. It means TV1, TV2, TVn is a basis for then TV, then we claim that W is spanned by TV. TV where TV is V1, TV2 up to TVN. Okay. Okay. Sorry. So B here we want to show that we claim that we claim that P dash is equal to we claim that V dash is equal to TV, TV1, TV2, dash dash TVN is a basis for W. Okay. Now B dash is linearly independent. Let alpha 1, alpha 2, alpha n belongs to field such that alpha 1 TV1 plus alpha 2 TV2 alpha n TVN is equal to 0. This implies P alpha 1 V1 plus alpha 2 V2 alpha n Vn. Since P is 1 1 and T0 is always 0, we get alpha 1 V1 plus alpha 2 V2 plus alpha n Vn has to be 0. But alpha V1, V2 up to Vn are linearly independent. We get alpha 1, alpha 2, alpha n is equal to 0. So this implies PV1, PV2, PV3, TVN are linearly independent. So this implies B dash is linearly independent. Second, so B dash is linearly independent. Okay. As dimension of V is equal to dimension of W is equal to N, and B dash is linearly independent, and cardinality of V dash is equal to N dimension of W. So this implies V dash is basis for W. Let W belongs to W. Since S is basis for W, we have scan V dash is equal to W. This implies there exists alpha 1, alpha 2, alpha n belongs to F such that W is equal to alpha 1 PV1, alpha 2 PV2, alpha n PVN. So by linear property of P, we have this one. So put B is equal to alpha 1 B1 plus alpha 2 B2 alpha n Bn. And this element here belongs to B because B1, B2, Bn are basis elements. In basis, means they are in B. Then W is equal to PV. So this implies P is on to. Conversely, assume that P is on to. P is on to. If possible, suppose that P is not 1, 1. Okay. So we know that P is 1, 1 if and only null space of P actually contain 0. We will prove it. We will prove this in the last of the lecture, the last of this lecture. Okay, we will prove it in the last of it. Now we have this fact. Uh, in other birds, in other birds, T is not 1 1 means not 1 1 if only if null space of T is not equal to 0. Okay. Since T is not 1 1, we have null space of T not equal to 0. But T at 0 is 0. So this implies 0 always belongs to null space of T. So this implies there and null space is not equal to 0. It means this implies 0 properly containing null space of T. So this implies there exists V belongs to V. There exists V belongs to V. Null space of T, V is not equal to 0. Since this set is linearly independent, we can extend V to a basis V dash basis of V. It means there exists a basis V is equal to V1, V2 up to Vn minus 1. Because dimension of V is actually n minus n. So it will contain, basis will contain n elements. Because this basis extension of B, so B will contain in this basis. Now, let W belongs to W. Since P is on to where exists B dash belongs to B, such that P V dash W is equal to T V dash. Now, V dash belongs to B. There exists alpha 1, alpha 2, alpha n belongs to F such that V dash is equal to alpha B alpha 1 v1 plus alpha 2 v2 alpha n minus 1 b n minus 1 because span of b is equal to b as b is basis for v. Okay, that is why this is happening. So this implies W is equal to dv dash d alpha b plus alpha b1 plus alpha 2 v2 alpha n minus 1 v n minus alpha tv plus alpha tv1 plus alpha 2 tv2 alpha n minus 1 tvn minus. Okay, but because b belongs to null t, this implies tv is equal to 0. Okay, so so this implies w is equal to alpha into 0 plus alpha tv1 alpha 2 tv2 alpha n minus 1 tvn minus. Okay, so this implies w is equal to alpha 1 tv1 plus alpha 2 tv2 alpha n minus 1 tvn minus. So this implies w this implies w is a span of tv1 tv2 tvn tvn minus 1. So this implies dimension of w is less than equal to n minus 1, which is a which is a contradiction to the fact that dimension of w is actually n. So why this contradiction is coming? Because we have assumed that t is not 1. So this implies t is 1 1. Okay. So corollary, let v and w be two vector spaces over the same field f such that dimension of v is equal to dimension of w and that is finite. If t v to w be a linear transformation, then the following are equivalent. then the following are equivalent. First, T is 1, 1. Second, T is on to. T is 1, 1 and on to. So 1 and 2 are equivalent. Okay. So this corollary follow immediately from corollary, oh, sorry, theorem. Because if T is 1, 1, then it is on to. And so 1 implies 2. So if T is on to, then T is 1, 1. So third follows. And from third, 1 follows. So 1 and 2 and 3 are equivalent. Now we are going to prove the last result we have used in the theorem. Let V let V and W be two vector spaces over the same field F, and PV to W be a linear transformation. Then P is 1, 1 if and only if null space of T is equal to 0. Proof. First, assume that T is 1, 1. So let V belongs to null of T. What is null of T? V such that TV is equal to 0. As V belongs to null T, null T. This implies TV is equal to 0. But T is a linear transformation. We have P0 and 0 is equal to 0. So this implies PV is equal to P0 is equal to 0. So this implies PV is equal to P is 1, 1. We get V is equal to 0. So this implies null space of T will be exactly 0. Because you taking any element from null space, that is going to be 0. And 0 containing null space. So null space will be exactly 0. Now, conversely, assume that null space of T is 0. Now let V1 and V2 belongs to V such that TV1, TV2. TV1 is equal to TV2 So this implies T V1 minus T V2 is equal to 0. So this implies T V1 minus V2 is equal to 0. So this implies V1 minus V2 belongs to null T. But null T is nothing but it contains 0. So this implies V1 minus V2. So this implies T is 1, 1. So remark that V and W be two vector spaces over the same field F, and T V to W be a linear transformation. Then T is not 1, 1 if and only if null space of T not equal to 0. In other words, in other words, T is not 1, 1 if and only if 0, 0, null T. Because 0 belongs to always null T, and null T not equal to 0. Okay. So today's lecture to this, if you have any comment related to this, you can comment on my YouTube channel. Like, share, comment, and subscribe my YouTube channel. So thank you very much for today's lecture. Thank you very much. We will see you for next lecture.